Hey guys, welcome back to another lecture video for Chem 115. In this lecture video, we will discuss what Le Chatelier's principle is and how different stresses, when applied on a chemical system, will shift the equilibrium in favor of the forward direction or the reverse direction, or perhaps neither of the two. Now, to better understand this topic, we have to keep in the back of our mind that this chemical reaction is already at a state of equilibrium. And so this can be demonstrated graphically, where the concentration of the reactants and products is on the y-axis, and the progress of the chemical reaction with respect to a unit of time is on the x-axis. And so if I draw your attention to this specific period of time, I want you to notice that the concentration of the reactants and the concentration of the product are constant. And so this is telling us that this chemical system is at a state of chemical equilibrium. And so what we want to address in these next few lecture videos is if we apply some type of stress on a chemical system that will inadvertently disturb the current equilibrium, what would the chemical system have to do so as to reach a new state of chemical equilibrium? So let's go ahead and start understanding the different types of stresses that we can apply to a chemical system that's already in a state of chemical equilibrium before we discuss how the chemical system will counteract that change. So overall, there are four main stresses that I will be covering in greater detail, and that is the change in concentration of reactants and products, change in pressure and volume, change in temperature, and the addition of catalyst to a chemical system that's already at a state of chemical equilibrium. And so once again, these are the four main stresses that I'm going to discuss in greater details over the course of a few lecture videos. Now there is a fifth stress, and that is the addition of an inert noble gas. And so I'm not going to discuss this stress all too much. I'm just going to go ahead and give you the outcome. In other words, it does not shift. Adding an inert noble gas to a system under constant volume will not shift the equilibrium one way or another. And so the reason that is because the addition of this non-reactive inert gas doesn't really change the partial pressure of the other gases in the container. And so therefore, the addition of inert noble gas under constant volume will not shift the equilibrium. If we are under constant pressure system, then that changes things a little bit, but that's going to be for a different story. We're not going to be focusing on the condition in which we have constant pressure. And so we're just focusing on constant volume for the addition of inert gas, and overall there is no shift in the chemical equilibrium. And so overall, if we were to apply any of these stresses to a system that's at a state of chemical equilibrium, Le Chatelier predicts that the chemical equilibrium will shift in such a way that counteracts the disturbance that was made. And so the first stress that I want to discuss in greater detail is concentration, changes in concentration. And so I'm going to go ahead and use an analogy to better convey how the equilibrium will shift depending on the stress that was applied on the chemical system. And so the analogy that I'm going to be using is this tank, these two tanks that are connected to each other. And so tank A, which is the left side, is going to represent the reactants. And tank B, which is on the right side, is going to represent the products. And so I want you guys to notice that the level of the liquid is equal between both of these tanks. So currently this system is at a state of chemical equilibrium. So what would happen if we were to disrupt this equilibrium by increasing the level of the liquid for tank A? In other words, what if the stress that we are applying is to increase the concentration of the reactant? And so if we just focus back on the analogy and let this play out, if we increase the level of the liquid for tank A, at some moment in time, it's going to look like this, where the level of the liquid in tank A is going to be different than the level of the liquid in tank B. And so if you allow gravity to do its thing, then we know that the liquid, the added liquid that's in tank A, is going to eventually make its way into tank B until the water level, or until the level of the liquid, is once again equal. Okay. And so overall, there was a net shift in the direction of this liquid moving from tank A to tank B. And so we're going to say that the equilibrium will shift in the direction of the production of products. And so let's go ahead and tie this back in to a chemical reaction. And so if a chemical system is at an equilibrium, and if we add more reactants, then to reach a new state of equilibrium, the reactants that was added to the system must be consumed. And so the consumption of the reactants is demonstrated by the movement of the water level going down and essentially flowing into tank B, where the level of the liquid in tank B will go up. Okay, and so since there is a net increase in the amount of products, then we would say that overall the equilibrium has shifted to the right. And so there is an overall favor of increase in the amount of products at the new equilibrium state. Okay, and so overall, the new equilibrium will be reached, and the way that was done is that products is produced at the cost of consuming reactants. All right, and so let's go ahead and look at another stress. And so we're still focusing on tank A here. And so instead of increasing the level of the liquid for tank A, we're going to decrease the level of the liquid in tank A. In other words, we're going to decrease the amount of the reactants, because tank A is representing the reactants in this analogy. So going back to this illustration, we can go ahead and demonstrate this by puncturing a hole in tank A. And so this is going to be the stress that's applied. Right? We're puncturing a hole in tank A, and we know that if we have a hole in a tank, the level of the liquid is going to decrease because it's going to flow out of the tank. And so at some point in time, there's going to be an unequal amount of level between the two liquids in tank A and tank B. And so if we allow this scenario to kind of play out in our mind, and if we allow gravity to do its thing, the water level or the liquid, the level of the liquid in tank B is going to go, it's going to flow from tank B into tank A. And so overall, there's going to be a net shift in the direction of tank A, which is representing the reactants. And it's going to do so until a new equilibrium is reached. Okay. And so let's go ahead and redo this analogy with respect to a chemical reaction. And so if we have reactants and products, if we somehow decrease the amount of reactants through either precipitation or evaporation or what have you, then the chemical system will shift in such a way that it's going to consume products to compensate for the amount of reactant that was lost. Okay, and so through the consumption of products, we're able to increase the concentration of the reactants until a new equilibrium is reached. Okay, so that's basically what I've described there. So overall, there's going to be a net shift in the direction of the reactants when the amount of reactants is decreased. All right. And so we've looked at a couple of scenarios for changes in concentration, but we only focused our attention to the reactants. And so the next two scenarios, it's going to be similar to the previous slide, but this time we're going to be focused on the products. And so once again, we have tank A and tank B representing reactants and products. And the chemical system is at a state of equilibrium. And so for this specific stress, we're going to go ahead and add product. In other words, we're going to increase the level of the liquid in tank B, which represents the products. And so at some point in time, we're going to get an image that looks like this. And if we allow gravity to kind of play out, we know that the liquid inside tank B is going to decrease and flow into tank A. And when this liquid flows into tank A, the level of the liquid in tank A is going to increase. And so since there is a net increase in tank A, we would say that the equilibrium will shift in the direction of the reactants when we add more product. And so if we talk about this in the perspective of a chemical reaction, if we increase the amount of products, then for a new equilibrium to be achieved, the products that was added will be consumed, thereby producing more reactants. And so overall, we have a net shift to the left, meaning the equilibrium will favor the production of reactants at the cost of the products, at the cost of consuming products. So looking at our last scenario, here we have tank A and tank B once again. The disturbance or the stress that's applied to this chemical system would be a decrease in the amount of product. And so in other words, we're going to puncture a hole in this tank that's going to decrease the amount of liquid in tank B. And so at some point in time, this is what the water or the liquid level will look like for tank A and tank B after some amount of tank B was removed. And so if we allow gravity to play out, we know that some of the liquid will pour from tank A into tank B. And when the liquid pours into tank B, it's going to increase the level of tank B until a new equilibrium is obtained. And so with respect to a chemical reaction, if you were to somehow remove, if we were to somehow decrease or remove product through precipitation or evaporation, then the chemical system will respond by consuming reactant to produce more product. So it's basically trying to compensate for the product that was lost through precipitation or evaporation or what have you. And it's going to keep on doing so until a new equilibrium is reached. All right. And so hopefully by going through this illustration of tanks and levels of liquids, you guys kind of understand how the equilibrium will respond to the stress that was added onto this chemical system. And so I want to go ahead and discuss the effect of concentration. However, this time I want to go ahead and utilize a different perspective. And so instead of drawing out tank A and tank B and all of that stuff, I want to go ahead and take a look at an actual chemical reaction with some numbers for the reactants and products. And so we're going to look at the effect of concentration through the addition of reactants. So this is going to be the stress that we're going to apply. So looking at this chemical reaction, here we have the conversion of hydrogen gas and iodine gas into hydrogen iodide, and hydrogen iodide decomposing to produce the reactants. So what I have here in this diagram is the amount of each substance that's at equilibrium before the stress is applied. And so here we have 5 hydrogen gases, and notice how there's no units. So you can either put in 5 molecules or 5 moles or whatever, what have you. So I'm just keeping it open for now. And so here we have 5 H2 gases, we have 4 hydrogen iodides, and we have 3 iodine gases. And so this is the equilibrium concentrations for this specific reaction before the stress is applied. And so what I'm going to go ahead and do is add reactant. And so I'm going to go ahead and open the lid, and I'm going to go ahead and add a hydrogen gas. And so even though I just added 1 molecule of H2, you guys can interpret this as 1 mole of H2, which is 6.022 times 10 to the 23 power. And so I just don't have time to write a mole of H2. So I'm just going to draw 1 H2 molecule. And so this addition of H2 is going to disrupt the current equilibrium that this chemical system has achieved. And so according to Le Chatelier's principle, it's going to counteract the stress that was applied. And so since we added H2, the only way to counteract the addition of H2 is to consume it. So the counteraction is going to be the consumption of what was added, which in this case is H2. And so according to the chemical reaction, the only way to do that is if H2 reacts with I2 to produce HI. And so I'm going to go ahead and circle these two, and they're going to produce HI. And so since I consumed, since I consumed this I2, I'm going to go ahead and erase this because that's no longer present. Okay, and then notice how the H2 is gone as well. So let's not pay attention to the stoichiometry for now. This is just an illustration, so it doesn't have to be exact. If you want to be a little bit more precise with the illustrations, you can go ahead and add in more H2s, I2s, etc., etc. All right, so if we kind of tabulate what we have, here we have 1, 2, 3, 4, 5 HIs. And so I'm going to go ahead and write 5 HIs. And here I have 1, 2, and I don't see any more I2s. And so I'm going to put in 2 I2s. And here I am going to see 1, 2, 3, 4, 5 H2s. Okay. All right, so let's go ahead and take a look at what really changed between the first equilibrium and the new equilibrium. So I want you guys to notice that the concentration of HI effectively increased at the cost of the consumption of I2. And, you know, H2 was also consumed, but we're not counting it. And so notice that the amount of H2 kind of stays the same at the new equilibrium compared to the old. And so overall, since we have an increased amount of HI, we can confidently say that the production of products is favored. And so therefore, the equilibrium will shift to the right to counteract the addition of this H2 gas. And so I'll go ahead and write that overall production of products is favored. Okay. And so therefore there's going to be a net shift, or the equilibrium will shift to the right. Okay. And so we can go ahead and represent what happened in this scenario through this graph. And so I want you guys to notice that the concentration of H2, HI, and I2 is constant here. So this is the first equilibrium, right? So first equilibrium. And so this little increase is the stress. So there's an increase in H2. And so to counteract this stress, I2 will be consumed as well as the H2. So notice how the slopes are kind of both pointing down. So H2 will be consumed as well as I2, which are both reactants. And at the same time, products is going to be produced. So notice that there's a difference in the concentration of HI between the first equilibrium and this new equilibrium. And there's also a difference between the concentration of I2 at the first equilibrium compared to the new equilibrium. Okay? And so that's what we observed in this diagram, or in this, this image. So overall, the moral to the story is that the addition of more reactant will shift the equilibrium to the right, favoring the production of more products to achieve a new equilibrium. All right, and so we're going to go ahead and play out this same scenario. And this time we're going to be removing a reactant. And so we're going to go ahead and reset the simulation. And so here we have 5H2, 4HI, and 3I2. And so when removing this reactant, since they're gases, maybe we can like evaporate like one of the gases. And so I'm going to assume that H2 and I2 have different boiling points, and the differences in boiling point will allow one of those reactants to kind of evaporate away if we were to start at 0 Kelvin, something like that. Anyways, so let's go ahead and take this H2 and we're going to remove it. So here we have the removal of this gas. And so when we remove this gas, let's see here. So to counteract the removal of H2, we need to increase this H2. We need to compensate what was lost by consuming the substance that's on the other side of the arrow. In other words, we're going to consume hydrogen iodide. So we're going to consume product to counteract the removal of H2. And so we're going to go ahead and demonstrate this by erasing first, where we need to erase H2. So notice how H2 is now gone. And since we're going to consume product to counteract the removal of H2, that means we need to remove one of the HIs. And when we remove one of the HIs, then we're going to get back H2, and we're also going to get I2. Once again, let's not talk about the stoichiometry. We're just simply going to replace HI with H2 and I2. Okay? And so let's go ahead and tabulate the amount that's left over. So here we have 1, 2, 3, 4, 5. Okay. So here we have 5 H2s. Let's talk about I2s. 1, 2, 3, 4. I believe that was it. So I have 4 I2s. And here we have 1, 2, 3. So we have 3 HIs. So once again, I want you guys to notice the difference. At the first equilibrium, before the stress was applied, we have 4 HIs, and now it decreased to 3. And after the stress was, after we consumed the product to counteract the stress, we went from 3 I2s to 4 I2s. And so overall, there's going to be a net increase in reactant and a net decrease in product. And so therefore, we can confidently say that the equilibrium has shifted to the left to favor the production of reactant and a decrease of product to reach a new state of equilibrium. Okay. And so this left and right that I'm referring to is with respect to this chemical equation, right? So here we're shifting to the left, consuming the product so that we can counteract the removal of H2 gas. And so we can go ahead and diagram this by using this graph. And so I want you guys to notice that the stress was applied at this point in time. And so this region right here is more or less the response. Oops. And this region right here is going to be the new equilibrium. Okay. And so let's go ahead and follow it through. So here we have a decrease in hydrogen gas. And so to counteract that stress, we're going to consume product. And when we consume product, the concentration of H2 will increase, which is what we're looking for. We're trying to replenish what was lost. But at the same time, we have an increase in I2. And so this graph describes the same thing that we're seeing here. And so overall, the removal of the reactant will shift the equilibrium to the left, favoring the production of more reactants to achieve a new equilibrium. All right, and so hopefully by going through these two examples, you guys are kind of understanding how changes in concentration will affect the chemical system such that either the chemical system will favor the production of reactants to reach a new equilibrium or favor the production of products to reach a new equilibrium. And so there's a couple more examples that I'm not going to go through in this lecture video, but I will finish this. I'll finish these two examples, and you guys should see the finished product on Canvas. So let's go ahead and apply this theory to a chemical reaction. So here we have an equilibrium where we have this metal complex, this copper metal complex, and it turns out that the color of this is blue, and we have this metal complex in which the color of this is yellow. And so let's just say that they're at an equilibrium. And so if you mix blue and yellow, it makes green. So if you see green, then you kind of have equal amounts of these two. And so what if you add hydrochloric acid to the system? How does adding hydrochloric acid to the system affect the equilibrium and what color will be observed? Okay. And so I'm going to write a couple stuff here. So blue plus yellow makes green. And so that's telling us that we have equal amounts of the reactant and product. All right, and so if we add hydrochloric acid, HCl, what color will be observed? All right, and so to better understand the addition of HCl, we need to go ahead and recall or review our solubility rules. And so if you recall from the first semester of general chemistry, if you have hydrogen, if you have some type of acid basically, the physical state of matter is going to be aqueous. And what that means with respect to this specific example is that the addition of hydrochloric acid into this solution will force HCl to separate into their ions. And both of them are going to be aqueous in state. And so what we're really doing is we are adding H plus and Cl minus. And so if you add H plus into this beaker that's filled with this solution, it won't really affect the concentration of any of these because the identity of these chemical formulas is not H plus. And so we're not adding H plus exclusively when we add HCl to this solution. What we're doing is we're also adding Cl minus. And so if we add Cl minus, notice that in the chemical equation, chemical reaction, Cl minus is a reactant. And so overall, we are increasing the concentration of Cl minus. And since the Cl minus is a reactant, increasing the concentration of this is going to shift the equilibrium to the right. Remember, so this increase of Cl minus is the stress. So here we're adding reactant. And when we add reactant, that's telling us that the equilibrium will shift to the right so as to counteract the addition of this reactant. And so overall, the equilibrium will shift to the right. Thus, yellow will be observed because now we're favoring the production of products. Okay? All right. So let's go ahead and take a look at another example. So we're still working with the same chemical reaction, and we're going to assume that this reaction is the color of this beaker is green. And so basically you have equal amounts of all of these substances, just for argument's sake. And so how will the equilibrium shift if we add lead to ion? And what color will be observed? And so once again, to better understand this, we have to review our solubility rules. And if you guys recall your solubility rules from the first semester of general chemistry, in the presence of a chloride, so lead to ion, in the presence of a chloride ion, will produce lead to chloride, which happens to be precipitate. And so what you're doing is you're taking away Cl minus in solution to produce a precipitate. And this precipitate is solid in state. And so let me put in some physical states of matter here. So notice that so this two kind of is the same. It's the same ion, same physical state of matter. And so what you're doing is you're removing the free chloride ions. And so to compensate for the loss, then the reaction, the equilibrium will shift to the left. In other words, it's going to consume some products to compensate the amount of chloride that was lost. And when the products are consumed, not only does it increase the concentration of Cl minus that was lost, but it also increases the concentration of the other reactant. And so therefore, the color blue will be observed at the new equilibrium. And so basically this will shift the equilibrium to the left so that more reactants are produced. Okay. And so once again, we're trying to counteract the stress. And so at the very end, we're going to see blue observed at the new equilibrium. Okay. All right, and so reviewing your solubility rules will definitely help you guys out for these types of problems. So please, please, please go ahead and do that in your own time. And so last but not least, let's go ahead and talk about the addition of water. So we're going to go ahead and restart this scenario. So here we're going to go ahead and see green, meaning that we have equal amounts of everything. And so if we add water, what color will be observed? So how will the equilibrium shift and what color will be observed? And so here in this case, since we're adding water, so we're increasing the amount of H2O. So it turns out that H2O is a product. And so in this case, since we're increasing the concentration of the product, Le Chatelier's principle tells us that the equilibrium will shift to the left to counteract the stress that was applied to the chemical system, which was an increase in water. And so overall, the equilibrium will shift to the left to counteract the addition of product, which in this case just happens to be water, because that's what we added. And so the color that we're going to observe at the new equilibrium is going to be blue. Okay. And so I want to go ahead and just talk about water just a little bit more. So here in this scenario, water is an actual product. And so if we add more water, it's going to shift the equilibrium to the left automatically. But what about when water is not involved in a chemical reaction? In other words, it's not a reactant nor is it a product. And so it turns out that the amount of solvent, or water in this case, still affects the equilibrium, even though it's not an actual reactant or product. And so let's go ahead and see how the reaction system will shift when more solvent is added. And so if we're adding water, and if we're treating water like a solvent, so we're adding solvent to the chemical vessel, the equilibrium will shift in such a way to increase the total concentration. And so the increase in total concentration is the way that the chemical system will counteract the stress. And so if you guys think about this, if you are adding more solvent, you're basically diluting the system. And so the only way to counteract a system that's diluted is to increase the concentration. And so for this specific example, if we increase the volume of water, which happens to be a solvent, it's not taking part of the chemical reaction. Let me zoom in. The chemical system will, the chemical system will shift in the direction of more substances, thereby increasing the total concentration of the system. And so notice that here we have 1 iron, 1 thiocyanate, and 1 iron thiocyanate. And so here we have 2 reactant particles. So here we have 2 particles, and we have 1 particle. And so, let me just rewrite that again. So we have 2 particles. We have 1 particle. And so to increase the total concentration to counteract the stress, the equilibrium will shift to the left. Okay. Now let's go ahead and talk about the opposite scenario. Once again, if solvent is not involved in the chemical reaction, if we somehow remove the solvent through evaporation, how will the reaction, how will the chemical system compensate for or adapt to the stress? And so in this case, the chemical system will favor the side that will allow you to concentrate. If you remove the solvent, you're concentrating the solution. And so I apologize. So if you're concentrating the solution, that means that you want to dilute the solution. And the only way to dilute the solution is to shift the equilibrium that favors the lesser number of particles in the solution. So to counteract this, you want to lessen the number of chemical species in the solution. So that way the solution becomes more diluted. And so in this scenario, if we're going to remove solvent, the equilibrium will shift to the side that has a lesser number of species. And in this example, it's going to shift to the right because this has the lesser number of particles. Okay. All right, so that's pretty much it for this lecture video. I know it's kind of long and lengthy. And so hopefully you guys were able to understand my train of thought, my logic with respect to how changes in concentration, whether it's a reactant, a product, or a solvent, will affect the chemical system. And you guys hopefully are now able to predict how the equilibrium will shift to counteract the stress that was applied. All right, guys, I'll see you guys in the next lecture video. Bye.